And this is how the stiffness matrix was generated. And we explained this, that any ijth element of the stiffness matrix can be denoted by Kij, which is the force required to be applied at ith degree of freedom to create unit displacement at jth degrees of freedom. If you talk about K21, that means it is the force required to be applied at second degree of freedom to create unit displacement at first degree of freedom. So this is the meaning of K21 and zero displacement at all other degrees of freedom. So when we are considering this figure, that means we are giving only unit uh, deformation along the first degree of freedom, and then there will be a tendency of this point to move with that. So we have to apply a fixing of force in order to maintain zero displacement at all other degrees of freedom. And then we are generating, in this process, we are generating the first column of the stiffness matrix. So in the same way, this figure is for second degree of freedom. That means we are applying unit displacement at jth degree of freedom and ensuring that degrees of freedom at any other that the displacement in any other degrees of freedom are zero, to ensure that these are the kind of the shape which we are getting from this figure. So the first figure, from the first figure, considering the forces, we are getting the first column of the stiffness matrix. From the second figure, we are getting second column of the stiffness matrix. From this figure, last figure, we are getting the third column of the stiffness matrix. So in fact, we discussed it. So I'll request you, can you write down this stiffness matrix, seeing this figure, just taking 5 minutes time. Can you please try to do this? Okay, so what's happening is, for this particular case, you'd see that these are the deformed shapes we have considered. I mean, and this is for the first case, that is for generating the first column. This is for generating the second column, and this is for generating the third column we considered. And then if we write down the value numerically, or otherwise if I just put the values of K1, K2 and K3 here, then ultimately we are getting this stiffness matrix as 10 to the power Newton, 9 Newton per millimeter outside, and then inside the matrix, these are the numbers. And of course, this stiffness matrix or the mass matrix, what we are getting, all of them are of symmetric nature. And what should be the size? In this particular case, we are proceeding with 3 degrees of freedom. Therefore, the displacement vector will consist of these 3 elements. And how we'll decide this number? We know that the number of natural frequencies which will come, that will be nothing but equal to the number of degrees of freedom we are considering. And therefore the problem size will be also in the order of 3. If we would have considered 5 degrees of freedom, it would have been in the order of 5, and so on. Understandable? Any question up to this? So we will try to first, to understand the dynamic characteristics of the structure, we'll try to first study the free vibration equation. That means M matrix into acceleration vector plus stiffness matrix K into displacement vector is equal to a null vector. And so if I numerically write down, then this will be the equation. And now these equations are called set of simultaneous coupled differential equation, which we were discussing at the time of 2 degree of freedom system. When degrees of freedom will increase, you then try to realize that, well, by God's grace, we are getting 0 and 0 here for this particular problem. Otherwise, if we would have got non-zero terms, then maybe that in one equation, more than one variable, maybe 3 or 4 variable are maybe if this vector would have been x1, x2, x3, x4, and so on. Here is a mistake. So on, then those terms would have been present in the first equation itself. So it would have been of very much coupled nature, and that really poses a problem. So there are two types of solution. One is analytical solution, and the other is numerical solution. And the very accurate analysis which we can carry out is called the modal analysis. That means, as I have discussed, that the basic consideration is that at any instant of time, the displacement vector is a combination of the independent mode shapes into a time function which is acting as a weighting function for that mode shape. And with time, the weightage ratio, that means the ratio of participation of various modes in the displacement vector is changing. Okay, and we have to find out those. First, we have to know the natural frequency and the mode shapes. That will come from structure side. That is the input from structure side, and then the time functions which are acting as a weighting factor to the mode shapes. They are basically being decided by the external perturbation, which is, or the time varying force which are responsible for the vibration of the system. In fact, then we can carry out two types of modal analysis. One is time history analysis. We'll see that it is very, very rigorous. I mean, in 3 degrees of freedom, we'll try to show the example, and then possibly we'll not be able to go to complete it. At some level, we'll say that. Then after this, the procedure will be like that. But it will be such a cumbersome procedure. There is not very much intelligence involved in that, but it's a routine cumbersome procedure. One has to carry out that. It will be too much even for 3 degree of freedom system. So forget about the reality where we very often have, say, 50 degrees of freedom or so. And another is response spectrum based analysis. You already have the concept of the response spectrum, which gives us the response spectrum means the maximum value corresponding to the natural period of the system. So in this response spectrum analysis, it will not be that rigorous, but we will only get the design value, or otherwise speaking, the maximum value multiplied with adequate factors, adequate safety factors. So mostly response spectrum based analysis is practiced, and that is depicted in our code IS 1893 2016 version. That is the latest version, and I request all of you to at least to download this soft copy. Don't keep it in your computer. Please take a printout. Okay, you spend so much of money while having food in restaurant, doing new, I mean, buying new t-shirt and jeans. So instead of that small amount of money for taking the printout of these codes, IS 1893 part 1, 2016. That is one code. And then the other code which you will require in your future related to earthquake engineering is IS 4326 and IS 13920. These are the codes which talks about uh, some problems which are not mathematical, but some it talks about the detailing of the structure so that the structure can behave in a more ductile manner rather than a brittle manner. Because always we prefer a ductile failure, because in case of ductile failure, after the yielding takes place, it gives a long plateau to take the plastic formation, and so it acts as a warning to us, and we can remove uh, all appliances which are there, and also the human beings can come out. But for brittle failure, it will suddenly fail. So the people, even before the moment of failure, will not be in a position to understand that the failure is going to take place. So, so you may stop here, and you may, if you have any question, you may please feel free to ask.